Kim today is going to be a little bit shorter than usual just because my chair's office has requested that I join a meeting about some stuff. So I have to go to a meeting instead of hanging out with you, which I must admit I'd rather hang out with you. Oh, Kim, you ruined my secret plan to make sure that there's a bar between me and the camera at all times. I guess I'll just have to wander this way a little bit more as I gesticulate. So, you know, when I say things like this, I can stand here and then... Anyway, so before we get started, I always like to know sort of the distribution of people in the class. What do you folks do? What programs are you in? Let's maybe start on this side.
Yep. I'm in general science. Psychology.
Psychology.
Cool.
Business.
Oh, awesome.
Science with like psych and cognition and language.
Pharmacology.
Pharmacology, cool.
Surgery.
Oh, okay. Nice. Okay, awesome. So I'm Patrick. I do a bunch of things. So you could say I'm in computing science. You could say I'm in medicine. You might say I do all those things. Maybe I do none of them well. But I'm going to try and give you a talk today. It's a talk I actually gave up in Whitehorse earlier for a national physiatry conference that gives more of a bird's eye perspective on artificial intelligence and how it might apply to medicine, but specifically how it might apply to rehabilitation. Does that sound okay? I promise I'll show you lots of cool videos. That's like the main bit of this is showing cool videos. But we'll also get into a few topics like what is this AI thing. I'm sure Osmar has already walked you through all of that. Osmar's given how many lectures?
So three.
Okay, so you're already pros at all of this, but we'll see as we go through the lectures. Sound like a good plan for the day?
Yep.
Okay, awesome. I'll also give you a demo of reinforcement learning. Did anyone give you a demo of RL before? Reinforcement learning?
No.
Oh. Okay.
About it, I haven't had a demo.
Okay, well I'll show you a very, very, very simple demo, and hopefully it'll be something that you'll find exciting. Cool. Conflict of interest there is none. So this is the main stuff. So what I'm hoping by the end of the next 40 minutes is that you'll maybe better than you already. I'm assuming you're already able to define AI and machine learning, but I'm hoping that you'll be able to augment your ability to describe those fields by the end of the time we're done today. Hopefully you'll be able to fill in some gaps in discussing the key characteristics of artificial intelligence and machine learning. The bit that maybe you haven't bumped into is the bit that relates to how AI has been applied to physical medicine and rehabilitation. So that's something I'm going to hope to give you today so you can get an insight into how AI is being deployed within society. This again was a lecture I gave to physiatrists, so you may not have a personal clinical practice, but I do want you to be able to estimate the impact that intelligent system technology might have on your own study or work within the next 5 to 10 years. And hopefully I'll give you some pointers into the appropriate literature, into the hooks into the literature that you can go to stomp around and find more about these topics. Okay, who's seen this video before? Anyone seen this video before? Ah, okay, cool, I like video. Oh yeah, I mean, you've seen this like every single year for, I don't know, quite a while now. This is part of the BrainGate trials, and so this is a study participant, Jan Schuerman, who's feeding herself the robot limb. So there's a couple of key points I just want to make about this video as we move forward, is that Jan is paralyzed from the neck down. So Jan lost the ability to move any of her body below her neck, and as part of this study, Jan is able to control this robot arm to feed herself a chocolate bar directly with her brain. So like, if you can see when the video comes back, you're going to see there's a couple of, there you go, those two gray plugs there. Those are gray plugs that actually clip into Jan's skull and connect to electrodes implanted in her brain. So Jan's actually got the Utah rays, it's a dense array of electrodes implanted directly on the surface of her brain and into the layers of her cortex. And she is using her brain to control that robot arm to feed herself. So even though she can't move her own biological body below the neck, she's able to volitionally control that robot arm to perform tasks of daily living. So you can see her feeding herself a chocolate bar. There's other sheets of silly string. She like fist bumps one of the doctors and puts shapes into a shape wall. So this is there's a shape wall there. So this is one example of advanced systems technology, and we're going to sort of tie this together soon. I just want to show you a few vignettes though of advanced rehabilitation technology, and then I'll tell you why I'm showing you these. Here's another one. So this is another kind of brain-body machine interface. This is a gentleman who has amputation, so at the shoulder level. And so you can see this is from Johns Hopkins University. This gentleman is using signals from his body, in this case his muscles and his reinnervated nerves, to be able to move both of those robot arms up and down and to control the hands, the elbows, and even the shoulders of the robot arms that are now attached to his body. He's lost both of his arms in an accident, and in this case, he's able to now be able to control 2 robotic arms that are attached to his body. Someone must have seen this video before? Or is that, am I showing you all new material? Oh, wow. Cool, okay. So you can go stomp around on YouTube and see a whole bunch of wild things. These are some of what I think are the most exciting in the last 5 to 10 years. And here's another one. This is something that's also very special. Again, someone who's lost a limb to amputation, who's controlling a robot arm. Hopefully the video will pause as soon as you see this gentleman pick up that ball, drop the ball in his own hand. But one thing that's important here, in the previous example, that gentleman had essentially sockets that mounted this robot arm onto his body. This gentleman actually has a direct mechanical attachment to his body. So that part of his elbow there, essentially they have a metal socket that goes directly into his bone. So they've drilled out and hammered out part of his bone and it affixed a socket into his bone. So he can take his robotic limb and clip it into his own bone structure. So now it's not just like strapping it on like you see with prosthetic users over the decades, over the centuries, actually over many thousands of years. You can see an old Egyptian prosthetic toe, and it was like this piece of metal that they slipped on top of their foot and lashed on with leather straps. Since the dawn of prosthetics, people have been attaching them by really just strapping them to their body. This is one of the first examples of how the prosthesis can actually be clipped directly into the bone structure of the human body. Here you can see that this person's controlling this robot arm with these bands on his upper arm. He's contracting his muscles and it commands the robot limb as to how to move and perform. But there's also examples of this where there's wires that actually run from this robot directly under the skin, through that socket, and attach directly to the nerves and the muscles inside. So essentially you get like a full clip-lock interface between the robotic appendage and the person themselves. Cool. This is a really neat, this one's especially quite neat. Also in the same vein of those brain gate trials, you can see here's someone else who also has a direct attachment to their brain. In this case, it's someone who can't move their body, and instead of controlling a robot limb, here they're actually controlling their own body. They're essentially autopiloting their own body using their brain through electrical stimulation. So by allowing wires to run under the skin of their bodies, and think of it like another synthetic electrical nervous system that runs under the skin. They're able to use their brain to send pulses to the body that allows the muscles to contract. Yeah, please.
So they're just like bypassing their spinal cord basically?
Totally. Yeah, and I mean this is a very different, it's not, sometimes you might see examples where they try to bypass the spinal cord and make little bridges so that nerves can talk to another bit. This is essentially saying, no, let's actually build a whole supplementary system that allows the brain to excite the muscles. In this case, it's through electrical stimulation. There's downsides like, hey, muscles fatigue really quickly when you zap them with electricity. Various other downsides, but in this case, it's quite neat. You can record and you can transmit to the muscles and the actuators of the human body. And in this case, the human brain is controlling those actuators. Kind of wild, right? This is all, maybe, again, no one's seen this either then, I'm guessing. All right, this is cool. And you must have seen something like this, though. Some must have seen someone controlling a wheelchair with their brain. Okay, good. At least one person, like, getting some traction. So this is, you can see this person has a brain-computer interface cap. This is totally non-invasive. There's no wires under the skin. There's no electrodes implanted in the brain. Measuring the electrical signals at the scalp, allowing this person to use those electrical signals to drive this wheelchair around. And in this case, the wheelchair and the person are driving together. So the wheelchair is also doing some like vision. It's trying to detect obstacles and help the person navigate through the world. So these are all examples, and I'm going to keep moving through these examples because they're getting closer and closer to what you might go to Best Buy and pick up on a weekend. Here's the next bit. These are actually recording devices that can be implanted like little grains of rice directly within the muscles of the human body. This, I think, is a primate model study, but there's people who've had these implanted for a large number of years now in several different trials. These electrodes essentially are, think of them like really long grains of rice in this case, they're getting better, but that live under the skin, can transmit to the surface of the skin, and so instead of having to worry about clipping stuff onto the body, you can just implant things and they will monitor the motion of the human body, monitor the muscles and the activity of the muscles, so that those activities could be used to control an assistive device. They found these to be long-term stable, that they've been implanted for, I think someone has them for over, don't quote me on this, but over a decade before having them explanted. So they're long-term stable within the human body. Unlike some of the brain-computer interfaces. The person in the brain gate trial that you saw earlier, she's had those electrodes explanted. They've removed them from her body because they were starting to break down and the brain was starting to reject their use. Peripheral interface devices like this don't break down quite so readily. So those are all things that were research trials. This is something that people with amputations can go and actually buy, or their clinic can actually prescribe to them. This is essentially a robotic prosthesis. This is something that you would see fitted in a hospital, like the Glen Rose Rehabilitation Hospital here in Edmonton. And it's using machine learning technology. So this is now we're getting towards where the AI fits in. And I'm going to tell you where it fits in a few seconds. But in this case, you actually have a commercial device. The person can put it on their body. There's no implants. It will learn about the person and about what they need and be able to help them open and close their hand or bend their wrist or bend their elbow. So this is a commercially, clinically deployed machine learning rehabilitation technology, robotic technology. It's not a research grade platform anymore. This is an actual platform that people use. And it really has gotten to the point that you can go and buy one of these. So remember that black band you saw, the guy with the osseointegration, the actual direct integration into his bone structure? There was 2 black bands on his upper arm. Those are myobands by Foundic Labs. They're $200 at your favorite online or physical retailer of electronics. You can go buy them. You can plug them by Bluetooth into your laptops, and you can control your PowerPoint slides using a flick of your wrist. So those are commercial grade systems. It used to be that as researchers we'd have to spend 60 or 100K to get these really fancy like muscle recording devices. Now you can go out to a store, buy one of these for a couple $100, slap it on, it'll record the muscles from your body and use it to control a computer. The Muse is another example. So you saw the person driving the wheelchair using signals from their brain. You can just go to, again, your favorite online or physical retailer and buy something called a Muse. And it's a very simple, like very low number EEG electrode headset. It records the electrical activity of your brain and unfortunately all the muscles around your brain, but it doesn't actually turn out it matters because it's still able to allow you to think about things and send input to an electronic device like your phone or your computer. So all of the core technologies that underpin many of those interfaces I showed you all along the way in that series of rehabilitation vignettes, they're all based on technologies now widely available. And what's important, and this is the bit that glues it all together, is that almost every single example I showed, in fact, every single example I showed you uses machine learning. There is some kind of machine intelligence that is gluing the person to the machine, that is interpreting the complex signals from the human body, be it the firing of 100 neurons that they're sampling from in the human brain for Jan to control that robot arm, to the EEG cap where the person is trying to control their wheelchair, to all of those muscle electrodes that they're using to control the movement of the robotic bionic limbs, to the way that you actually map that myo band to the control of your PowerPoint slides. Machine learning is a substrate that allows that all to happen. It's really the glue that is taking the human signals and turning them into control and communication interface for the computers or the technologies that people are interacting with. And this is big. This was never the case. Even 10 years ago, this was not the case. Yeah, please.
Do people need to learn what to think about in order to operate them?
The answer is, I mean, we had a great visitor from, by way of a digression, we had a great visitor from German Aerospace last week who made the point, and I really agree with him, this is Claudio Castellini from German Aerospace, saying that really when we think about prostheses and all the other human machine interfaces, it's very much a co-adaptation problem. And I believe that. And so what that means is that the device has to learn what to think about and how to communicate with the person, and the person needs to know what to think about or how to structure their own signals to best communicate with their other partner. Like you and I are moving a couch, and we're like, oh hey, a little to the left, or like you feel me sort of push the couch, which means maybe I'm trying to go forward. Some of those signals are more natural and intuitive, and we don't really have to think about them in an explicit sense, but some of those communication channels that the person and machine are using to co-adapt are actually very challenging, and they do actually have to like form something to think about. Like with the Muse, you're like, okay, I'm going to think about nothing, and that's really, really hard, so what can I think about? That maybe I think about throwing a tennis ball, and because this is like up here in my brain, then I don't, you know, like you try to figure out how to think about it. The other commercial grade EEG headsets, you can be like, I'm going to think about a cube, and then that gets mapped into a signal. I'm going to think about the smell of like fresh cut grass, and that's mapped into another signal.
And is that just based on where in the brain that it's happening? So
Yeah.
it's really a geographical thing?
Yeah, for the most part, although you can imagine that some of those are complex patterns, and that's the tricky bit. It's not like you're saying, oh, I'm just looking for it to light up like here or here. Instead, it's really more like, okay, what unique differentiable patterns are being created by these different thoughts, and for the muscles, for different like visualizations or different contractions of the muscles in the body, if that's where you're extracting signals. So sometimes there are complex learning, you have to like complex learning tasks for the person who's trying to engage with these systems. Does that answer your question?
Yeah.
Yeah. Yay, this is my main point. All these things involve machine intelligence and machine learning. And I really do believe this picture, Kim has seen this picture probably ad nauseum, but I like still showing to this day, and that I do really believe that the intelligent systems technology is the glue, is the thing that exists between the person and the thing they're trying to interact with, to try to manage this complex web of signals and meaning that they are both taking in and giving out. This is where machine intelligence has a very powerful case for improving our lives as humans. So we're going to step back a bit like this. Any questions in the last little run here? I'm just going to make sure I'm still on time. Perfect. Any questions in the last little bit there before we move on to the next bit? Nope. Nope. Okay, cool. All right. What are some hallmarks? We've been talking a lot about, say, machine intelligence. Like, oh yeah, that's a thing we can all really well define. Or artificial intelligence, which is a really silly term. So what are some, like, let's just step back from all of the silly terms we attach on them. What are some hallmarks of intelligence? Knowledge, knowing things, right? This is one thing we think is we hold as a foundation of intelligence, is that we've somehow captured or stored some of those regularities of the world so that we can regurgitate them later on a midterm exam for Med 590. This is the assumption that we know things. What was it? Game of Thrones, I drink and I know things? Sorry. Creativity, yeah, the ability to create new things out of the blue or out of the current stimulus patterns, create something you haven't seen before. So there's knowledge, there's remembering maybe, and then there's also creating something that isn't something you've remembered before. What else? Yeah?
Speed, like being able to regurgitate information relatively quickly.
Oh, yeah. You can imagine if you were a tape recorder storing everything that you've ever seen, and then trying to search through all of those frames, like a video recorder, a tape recorder, searching through all those frames and those audio samples for something, that seems almost impossible. So there's some kind of synthesis that allows you to be able to process information really efficiently, and then be able to respond in a moment's notice using those complex patterns. Like you see, hey, I'm walking through, I hear crinkle in the bush. There's a tiger. Okay, I've learned that crackles in the bush are related to tigers. You don't have to do some elaborate process to be able to make a good decision based on very complex stimulus. So yeah, that's a really good one. Anyone else? Memory, yeah, exactly. This ties really nicely to the last one as well. Remembering stuff is actually something we think that intelligent systems do. If I said, oh yeah, I got a great machine learner, what does it do? Oh, it sees stuff and then it forgets everything it's learned. And then it makes random decisions. We assume that memory is intimately related to knowledge and the ability to extract it, and the ability to create new things. Anything else?
Creating relationships between data.
Yeah. Some people even go so far as to call those relationships objects. I don't personally, but you might imagine that the brain does relate different pieces of information together, see how they all work. They work as a unit and they don't work as a unit, and then create even abstraction as well. I'm just going to throw various other relations and abstractions. Anything else? Decide maybe?
Like the ability to adapt to different.
I was waiting for someone to say adaptation. Absolutely, adaptation is a huge one. The ability to change, the ability to see a new situation, to change the way that you behave or the way that you process data. Adaptation is, I think, adaptation is learning. It's a very fundamental piece of what I think everyone agrees that intelligent systems have. Anything else?
Appreciation, the ability to appreciate what's just been done.
That's a tricky one. What do you mean by appreciate?
I'm not sure.
Yeah.
I say it more as a question.
Yeah, no one's ever suggested appreciation. I could be very technical. I could say, appreciation could be the assessment and realization of value. And if it's something like that, I think even the demonstration I'm going to show you in a few minutes appreciates value. In terms of being able to see a situation and be able to come up with an assessment of the goodness or badness of it, or
or in the case of humor, you can imagine that they could get the joke, but they can indicate the connections, but the question is, do they get? That's what I mean by appreciation.
So that's a deep. So as opposed to the appreciation in terms of value, the appreciation in terms of knowing goes back to knowledge, which is really hard. How do you? That's the old Chinese room experiment as well. Is it something just a fancy lookup table, or does it really know something?
It doesn't matter.
It doesn't matter. All right, cool. These are all great. So I'm gonna boil a lot of what's just been said down into a few other things. And those three things, the first three things I'm just gonna highlight. This is one slice through how you might want to interpret intelligence. It's actually different than the ones I've shown in previous iterations of the course. So that's like, I'm trying to provide new content, Kim, I'm doing my best. But a new way of thinking. One slice through what we mean by intelligence, usually I say it's like, oh, it's prediction, representation, and control, which you'll see next. But another way of thinking about intelligence is, you might imagine, it's the interrelationship between data and goals. And then decisions, the architectures, the decision and architectures that bring those two things together. And then going back to my old tricks, I'm going to argue that really that those things are facilitated by things like perception, the ability to take in stimulus, prediction, the ability to capture those regularities, the knowledge about the world, and to forecast how the future might unfold. And then action, being able to take those things and make decisions that interact with or change the world around you. I would say those are some of the hallmarks of intelligence that I think are most salient, at least for me in my thinking of intelligence. There's lots of them, we talked about a lot of them, but I think that these are some nice grounding blocks that we can use as touchstones. So with this in mind, let's play a game called Intelligent or Not. I'm going to flash things on the screen, and you're going to tell me, are they intelligent or not?
No.
No, toaster's not. Okay, cool.
Yes.
Yes.
Yes?
Is that a vacuum?
Everyone saying yes? Yeah, robot vacuum cleaner? Yeah?
Yes.
Yeah? Any no's? No? Okay. Amazon, or any of the other like Nest-like, Echo-like things?
Maybe.
Maybe? Yes? Yeah. No? Okay, good. That? Arguably no. That? It's a bipedal robot. It can speak multiple languages. It can pick up objects and put them in a dumpster.
Yes.
Yes? No? Good. Yes? Okay, cool. That's a great sample. I like that there was many yeses and nos that were said to the same things, because it's really tricky. And again, I first gave this particular talk to a largely clinical audience, and it's applicable to a wider audience because I would really like to try to address some of the common misconceptions about, especially artificial intelligence, that lead to all sorts of sensationalist reporting in the media, and also to a lot of misunderstanding by people who might need to or wish to deploy artificial intelligence technologies. And one of the most common misconceptions is, I think, this one. And it's that, like, intelligence is just a line, and then there's like a bunch of stuff at the end of that line that we all call AI. Like, people are somewhere down there, but that everything else is also down there, like the robot that can speak French and can like pick up objects and maybe do a little dance. The toaster, the voice recognition system like the Siri, or the robot vacuum cleaner. That often these are all A, put on a single line, and then B, all grouped together as the same thing. So you get a lot of reporting, and you get a lot of people that are unclear about the difference between something like a robot vacuum cleaner, which really takes in, like, it doesn't per se learn very much, but it uses a very straightforward behavioral policy to bump around your room and get all your dirt, just not you doing the vacuuming, to a system that can understand natural human language and be able to order you something from Amazon, to a robot that might be able to act and manipulate the world. Everyone groups those things together when I really want to make the point, these are fundamentally different things. They're different in many ways, and I heard you say you're going to talk to them again about ethics, which is fantastic, and there's ethical repercussions of how you think about these things. I hope you would agree. Yeah. The other bit here is that people often do this. Oh, okay, well we still have that, that big thin line of intelligence, like where this is not intelligent and this is intelligent. And then we go through toaster. Like the toaster, it keeps track of stuff. It has, like, it synthesizes data. It knows when it should pop your toast back up. Some of the smart ones will even try to detect if your toast is burning. There's the robot vacuum cleaner, which, will actually, in some cases, try to seek out dirt. I think even the fancy ones will do. Oh, that's good. Those are appliances though, right? And then you got like the robot, and no one will argue like, oh, something Boston Dynamics made is not, like, oh, that's AI. Yeah, look, that thing can open doors and can like use a drill to drive a car. Okay, well clearly that's intelligent. It's a self-driving car. But they're all still put along the same line. I'm going to say that's also a trap. It's a misconception that you could take intelligence, like we talked about all these different aspects of intelligence, everything from appreciating humor to creativity to remembering things and regurgitating them at speed. Like, can we really put these all in the same line? And that just seems to me kind of silly. And so I really want to convey this as maybe a more valid picture, or a picture that will serve us better when we're thinking about The Promise and Perils of Artificial Intelligence, as I think this particular teaching session is supposed to be titled. I think we need to truly appreciate the promise and perils of advanced intelligent systems technology, especially as we deploy it in our daily lives through things like self-driving cars or smartphones or medical technology or rehab technology, is that there's many different aspects of intelligence, and that all of the things we've talked about exhibit to lesser or greater degrees these different facets of intelligence. It's important, I think, to think of it like this. It makes it harder. It makes it harder to generate things down into a, well, that's AI doing this thing, and I think that's exactly the point, is that we need to think about what, how, and why the technologies we interact with are intelligent and are not intelligent. And when we think about how that impacts our lives and the lives of the other people around us, use that to make good decisions. So I just want to, this is the sort of the soapboxy part of this particular bit of the talk, is that I really want us to think about it like this. And I'm going to argue that if you think about how these systems acquire data, how they make decisions, and the goals that they are pursuing, or the way that they use that data to make decisions to pursue those goals. Again, perception, prediction, and action. I think that's a good grounding for how we might begin to see some of these different slices through intelligence, human and otherwise. Is that okay? We'll get a bit more into the definitions I promised you. Any questions on that last bit? No? Okay. Perfect. So let's just talk a little bit. So imagine that we do have machine intelligence. Imagine that we've defined it in sort of the broad class of things that I've presented so far. Why do people care? Like, why do we pursue machine intelligence as a thing? I mean, Osmar, I'm sure. What did Osmar tell you? Why do we do machine intelligence? Why do we do AI and data science and machine learning? What did Osmar say? I'm just curious, actually. Yeah.
I think he quoted that artificial intelligence is an enhancement of human creativity.
I like that. I think that's an optimistic and a very ambitious. I think that's very ambitious. That's the kind of line of work I pursue. So I'm inclined to agree with him. But that's well said. What else did you guys pick up from those other AI teaching sessions? Is everyone going back through their notes and checking? That'd be kind of funny if you were. Yeah, you are. Okay, awesome. Any other reasons why we should? Yeah, please again.
I think it helps us explore like many facets of like life and that we can't, that aren't directly accessible to us, such as data mining and using that information and building on it. Like that's not something we can just do ourselves, and we need that assistance to explore like how we can just use that to our advantage.
Yeah, I agree, and I think that's I hope that's what you got. I hope that was the gist of all of the previous sessions, because I do agree. I think I'm mostly saying the same thing here, and that like machine intelligence helps to. It's a big, wild, squishy, scary world out there. It helps to give us better control as humans over that changing and increasingly complex world. Maybe the world's as complex as it was before, but maybe we're just coming to realize how complex it is. It does something that I think we've wanted to do since people were rolling the knuckle bones of sheep or gazing into crystal balls and hoping to see something, some glimmer in the mist, is that machine intelligence also, by capturing those regularities, by building up that knowledge, by allowing us to synthesize it and bring it back in an efficient manner, it allows us to see the future. This is something we've tried to do for a very long time as a species, is to anticipate what's going to happen. Everything from farmers' almanacs to financial forecasters for the stock market. Machine intelligence gives us a better crystal ball. It actually allows us to better understand the patterns of the world and then see how those patterns may roll forward. And it gives some very general tools for solving some very, very hard problems. And this is everything from finance, healthcare, energy, resource transport, information processing. The list is going bigger and bigger. Your phones are all using, if you have an iPhone, there's a deep net on here categorizing faces of the photos, and so you can quickly find your friends or find a picture of a deer or a baseball. Like that's all machine intelligence, and it's all changing the way we do business. I'm just going to show this as an example of one of my recent graduating students trying to shake hands with the robot arm. And so I use this as a motivation for like going beyond just machine intelligence to actually the next little section. You can see that that's not a particularly natural handshake that Gotham is giving this much of a prosthetic limb. Our lab has failed since to make a better handshake, just to be clear. The premier was shaking hands with another one of our arms the other day, if you saw it on Twitter. Rachel Notley was shaking hands with the bento arm, and it looked something like this. It was really awkward. Why do I use that as a motivation is because now I'd like to actually say something a little bit about learning. So you could argue like that you could have intelligence without adaptation. I think it's a hard argument to make. I think you're right that adaptation is key, and learning I think is key to the kinds of intelligence we hope to interact with. And so why might we want to consider not just intelligence, but also learning as part of that intelligence? One really simple one is that things are unknown. Like, I mean, example I'll show you in the demo that comes up later is that we might know where we want to get to, but we might have no idea how to get there. I'm going to go like meet my wife after for dinner. I'm like, how do I get to the restaurant? Okay, maybe there's an intelligent system that can find the optimal way. In this case, it's called Google Maps. But you could, which also uses machine intelligence. But you know, you can actually start to ask the way that you might achieve an end that you hope to see. There's another bit though, is that you know we might even know like I don't know, I might even know more or less how I want to get somewhere, but now I can't really scale up. Like engineering problems are an example like this. It might be that there is actually a way you can apply a series of algorithms to figure out the mechanical stresses and strains on a gigantic bridge that goes like thousands of kilometers, and it goes, maybe it's a sky elevator, who knows. There may be ways that you could actually scale up all of our known, I'm just using engineering example, engineering principles to build that sky elevator, that infinite bridge. But it might be that it's just not possible to do this in a tractable amount of time. You could put a team of an infinite number of engineers working on an infinite number of like mathematical simulation computers, and it might still take you hundreds of years to make that awesome sky elevator. It might be that learning systems are able to more quickly scale up to solve those problems. Another is this, I think, is the adaptation, goes back to adaptation, is that things adapt. Like you drop a robot into the real world, like you have a pink dinosaur, you drop it in a classroom, you take it out and have it go try to catch Pokemon outside. It's going to be a very different world. Like it's not going to go do the Mewtwo raid because it just can't adapt to the changing world. It's going to be really good at interacting with this particular environment, but the environments that we interact with, our systems and us, change on a very regular basis. So learning is critical to systems adapting and be able to take on new environments. I'm going to do a quick demo now, is that right? Does everyone want to see a quick demo? I hope it works on these. I've had bad luck with these ECHA monitors, but I'll do my best. Because I want to show you reinforcement learning, because it's really learning through trial and error, and all things well, this should work. And this is this first example I'm going to show you is a very, very simple one. This is the world. This is the whole world of this little creature. And the creature is a black dot. It starts on this space where it's starting now. There you see an S as soon as it moves. And the goal, the G, is where it's trying to get to. And it's going to get reward for getting to the goal. Okay? And it's not going to like wander around forever. It's going to be uncomfortable for it to continue wandering in this world. It really just wants to get to the goal. And so what we're going to see is that this little learner knows nothing about the world. It doesn't know where the goal is. It can't see the goal, just to be clear. It can't see what the goal is. It has to explore the world through trial and error. It has to try to experience all these different situations and what it feels like to take actions in all these different situations until it's sort of like, think of it like digging holes in the ground. It's trying to find the goal that actually has the secret treasure hidden under the ground, in which case is that green G at the top. So you can't just see it from the get-go. And it's taking a long time, but eventually you can see it starts to figure out that there is a path to that goal. Now the path it's taking is pretty sad. I mean, it could do better. So if I make this go faster, you'll see that eventually, if we're lucky, we're going to figure out the faster way to go. No, it never does. This is just so sad.
This is doing this anew, or this is a fill note?
No, this is brand new. So I'm gonna mess with it in a second. So this is a really suboptimal way to get to the goal. But this is all it found. This is how it found out. And now it's really like, you can see the dark green that tells you how good or bad it thinks these different squares are. Like if you were in this square here, you see this is really bad, but you know that square is good, you're not going to go into that square. Similarly, this system has learned that. So if we want to mess with it, let's just mess with our little learner here. Ooh. Actually put walls in place. So this answers your question if this is a video or it's live. And we're being really mean. Like, what's it going to do? What I'm hoping you'll see, so let me just make it really mean. Eventually, it's going to speed you up. Trial and error learning is slow, folks. Eventually, it's going to find that. So eventually, it's through exploration. This is how the system is interacting with its world. Eventually, it's going to explore. It may only explore every now and then, but it's going to take an action that allows it to start to find the optimal path. There's something weird about the way this is running. I wonder if there's, anyway, not sure why. There might be some strange interaction. Usually it's found a better path than this. But let me just close this one for you. Where'd it go? No, go back. I need you to come back a little, there we go. Create a demo, GUI objects. Okay, and I'm going to open up a 6x8 grid world. This is another little world. You see this one as well. So what do we expect? We expect that through trial and error, it's going to eventually find that goal, right? Okay. So it just explored, it propagated back the right actions to do in the right situations. Now, as you would expect, if I do something, can I get to it? Sorry, the resolution is kind of wonky here. I can't get to it. Okay, I was going to make a little reward here and show you agent drug addiction, but I was going to show you like essentially a consumable award here that had very, very high reward that it could consume and get good reward. What you'd find is that if you start to put very transient high rewards in a world, that unless your agent's designed very carefully, it'll start to fixate on those like bright, shiny, big rewards and not be able to see the goal that's in the future. So you'll start to see some of the behaviors you see in people in a very simple black box that's running through a very, very simple grid world. Now you can imagine like, slow you down a bit so I can actually catch this. There we go. You would expect, again, this is just another, I'm just going to rerun this on a more complex world. We'd expect that eventually it's going to find that path on the top. If you see these arrows, those arrows actually tell you how good it thinks it is to move in any given direction from any given part of this maze. Eventually these arrows are going to shrink down to the point where it actually is okay taking that exploration, where it's going to step into that unknown territory. And now you can see how it's designed its arrows. It's actually, in this state, it says, now I'm going to go here, this is great. Oh, now up is really, really good. The arrows tell it the goodness or badness of taking an action in any given situation. There's something tricky here, though, is that if I were to do that, something's missing in this particular example. Because, I mean, it walks right by that opening, and it doesn't realize now that there's a faster way to get towards its goal. It doesn't see the obvious thing. And this is partly how it perceives the world, and partly how this particular learning machine is interacting. So I'm using this as an example. I'm going to stop it. I'll maybe let it go fast and I'll ask you questions. But I hope you can see how this is a complex interweaving of goals and of perceptions and of actions. Like, oh, well, that was pretty good. Looks like it actually took that step through. And eventually they'll find out. But this is a way, like the system has to manage how it is, essentially how it's taking its perceptions and flowing those through its decisions to achieve its goals. Anyway, is that okay demo? Is there any questions on the demo? Like, this is reinforcement learning in a very, very simple grid world case. I don't need to tell you about the algorithms or the ways it's interacting. I thought this would be a good way to get a feel for what it means for a machine to learn through trial and error. Any questions?
How does it know what the goal is?
It doesn't. So it only gets a single signal of good or bad, an actual single number, a scalar or a floating point number, which is either greater than or less than 0 or 0, like it's essentially a number. And this system is designed so that it wants big numbers. And it doesn't want small numbers. And so in this particular case, it gets the biggest number by going into that particular square. That G will be the point where it is able to actually get the most of that single scalar signal.
Does this go for all reinforcement learning? Is all reinforcement learning based on numbers?
Oh, that's hard. That's a very deep question. In the end, there is something called the reward hypothesis, which says that everything we can think about as sort of as goals or as drive really boils down to trying to maximize the long-term collection of a single scalar signal that we call reward. You can argue that there's things that there's differences around that topic, but in general, the idea is that at the root, reinforcement learning is a class of problems that involve learning through trial and error from a signal of reward. So like I say somewhere in the room, I'm like, hey, I want you to be somewhere in this room. I could tell you, hey, go to that corner, or I could let you wander around the room and like give you a cookie when you got to the back corner of the room. And you might learn over time that it's really important, really good for you to be in the back corner of the room. So that's, yeah, when we think about reinforcement, it's neat, it falls into that middle ground. Oh man, hey, look at that. We should found a shortcut. That there are problems where, on the previous slide, where you can start to think about how you might even get to a solution. Like you may know how to get there, you just can't really scale up your ability to solve the problem. Reinforcement learning is great when you know when you've succeeded, but you might not know how to succeed. Think of a robot arm trying to bring a coffee cup to your mouth and give you a sip. Like you know when you take a sip from the cup, but it could be like an octopus arm. It could be a really complex robot arm. It might be you're not a mechanical engineer or an electrical engineer. You don't know how to program the arm. So you could actually reward the system for properly getting the cup to your mouth. You may not know as an engineer or as a designer how to control the robot arm to do it, but it can figure it out itself. That's a good example of a reinforcement learning style problem. Cool? Okay, let's move on so I can dash. I'm going to be slightly late to meeting with the division chair, or the department chair. If that's okay. Is it okay if we move on from the demo? Because I think we're at a little bit of a faster bit. I want to wrap it up with a little bit of a discussion of how this relates back to physical medicine, rehabilitation, and medicine in general. Is that I think the kinds of technologies I've showed you, the things I've talked to you about so far, the idea that you can take data, you can take goals, put them together through a decision-making process, it does apply to our medical practice and in our wider society. And that let's just look specifically at medicine. Is that AI and machine learning help us to better understand populations of patients. So whole populations. At the population level, we can start to better generalize over massive sets of data. But it also helps us understand individual patients. So the robot arms I showed you are in effect actually fit to people. They're fit to individuals. Prescriptions are personalized to individuals. Machine learning and AI help us to better understand individual patients so we can treat them better. And also really it helps us to choose specific interventions. And this is where you can say like the dose of a drug or the exact prosthesis that you might want to attach to someone's body. We can help choose how to connect patients to the devices that assist them in their daily life, or how we deploy, say, rehabilitation strategies to help people get better more quickly. AI and machine learning are great for helping us generalize, personalize, and also optimize. The step through each of these in general, like really with patient populations, I think you can see this in our large electronic medical records. One of the hopes and dreams of these records is that we're able to mine salient information that helps us better treat all of the people in our province, in our country, in our world that have medical difficulties. We're trying to use that data as a society to better care for whole populations of people. At the individual level, this is just a video of some of our work with the prosthetics users, that you might want to see how different kinds of prosthetic users, red and green, compare to a population of people who don't have amputations. And then see how we can begin to take our interventions, choose which interventions maybe that we need to help people regain the ability to touch and feel and interact with their world. So we can start to look at where individual patients fit within that great sphere of data so we can treat them better. And in particular, specifically in choosing our interventions, again, we can look into the minds of our patients now with some of those technologies I showed you. We can begin to prescribe pharmaceuticals, we begin to assign physical technologies to people to help them live their lives better. And these intelligent system technologies can help us to better do all of those things. These are, again, the personalization, the generalization, and the optimization. In case you're really wondering what the robots are up to while we're doing all this generalization, optimization, and personalization, I'm sure you've seen this video. This is the Boston Dynamics Atlas robot. Yeah, you've all seen this video? Good, okay, awesome. For those who haven't, I think it's pretty spiffy, so I just want to show you, just to be clear, what the robots have been doing while we've all been busy building personalized prescriptions. And the answer is doing backflips. So yeah, it's all good. The robot's going to be busy for years. There's a lot of backflips they have to learn. And I like the blooper reel, actually. The blooper reel is, I think the next one is there we go. Let's see the bloopers. I'm gonna be late for my meeting, but that's okay. Let's watch the blooper reel. My favorite one is the second blooper. This one's like, you know, that landing was a little more shaky. Okay, that's adaptation. On some level, on a very primitive level, that's adaptation. So I like to haul it back. This is just hilarious. And that's what robots are up to. Don't worry about the robots. So let's just look again at this example. This is the demo I showed you that was using the dual modular prosthetic limbs to interact with the world. Because I want to make one last point before we wrap up for the day. And really that specifically in a medical context is that if we're looking to really treat the whole patient, if we want to treat the whole patient, and the patient's mind and body are both comprised of biology and technology, how do we do that? How do we actually treat the whole patient when the patient is both biology and machine? Like we see this with our prosthetic users, is that patients, if their technology is working, they consider their technology part of themselves. Like if I were to come over and smash one of your cell phones in front of you, your heart might jump and you'd probably pull away like it was your hand that was getting smashed. Like we've begun to consider technology part of our body. We have forever. Like humans have done this, animals do this. We consider our tools to be part of ourselves. And this is only becoming a more intimate relationship. Our biology and our technology is not easily separable. especially in clinical care, when you replace someone's arm with a robotic arm, when they lose their arm and you actually give them back a robot arm, you could say that that's not an easy thing to separate. When you remove that from their body, that's a physical and a psychological separation. For the same reasons, biological and technical care might not be separable. This is why it makes sense, I'm going to argue this is why it makes sense for me to be in a department of medicine as a computing scientist, is that the normal care of someone who is both biology and technology is going to involve people who are really experts in things like muscles and nerves and bones, but it also is going to be really important that people know the technology as well, that they know things about hardware and software and data science. If you have a person that is a very complex machine, a machine that's made of biology and of hardware as well, that we have to rethink how we give care and deliver care and how we actually treat the whole person. This is outside the medical realm as well. Because we've talked about this, and we've talked specifically through examples of connecting the human body to some kind of robotic appendage through machine intelligence. You saw examples of everything from wheelchairs to robotic arms. But I'm going to argue that this is more the case that we're looking at. When you think about my pitch to you about optimization and personalization and generalization, is that really we're allowing our own cognition to extend outwards in ways it never has before, to give into the world things that we hope to change and to take back information from the world and synthesize that. Whether we're a patient or a caregiver or a policymaker, we're using intelligent systems technology to expand our reach in the world. And that, I think, is really the key point of that's what I really want to share with you today, is I think this is the promise and perils of AI, at least in this particular context. So thanks so much. I think we have a couple minutes for questions. Yeah?
I was just going to ask, how do the neural networks of the human and the machine come to be compatible?
There are RS-232 cables, so you just take the machine, you plug it in, there's a socket right here, you get it at birth, you just have to pry off the skull. But don't worry, you've actually got a serial port right here. No, I'm kidding. Like, if you're asking how we very, very tightly glue together the human mind, the human neural network, and an artificial neural network, the answer that someone will give you will depend on their personal specialty. If you're talking to someone who is a biotechnology engineer, they'll probably tell you about the very nice, thin, like, highly efficient electrode that they're going to put into the nerve cell that they're going to wire into the spiky neural network. If you talk to someone like me, I will probably tell you that it's all about the information, the way information is shared between those two thinking systems. Like, that it actually doesn't really matter if you're talking about a biological system at the highest level, a biological system in a synthetic system, or two synthetic systems, or two biological systems, is that there is a way to start to understand the informational relationship between those systems. If you talk to someone else, you'll get a very different answer, like, oh, well, clearly it's going to be about how the brain is plastic and adapts to another system, or how the neural network is able to represent nonlinear concepts. So you'll see that we're talking about an interface, but all along the interface there are different problems at different granularities. I choose to think of it as an informational problem, in which case I have a artificial system that can perceive information. It has inputs, it can make actions, it has outputs, it can make decisions. I have a biological system. It can do those same things. And assuming that we have good physical interfaces, I'm going to assume my colleagues have got that covered, because there's a lot of smart people working on that. I'm not working on that particular piece. Then you're asking a question, well, how do we have two systems that can take actions and can perceive information? How do they start to communicate? How do they start to talk to each other? If we solve that problem, I think we solve all those problems. That's the big ticket. But that's my line of work, so of course I think that. Kim will think his line of work is the best line of work, and we all do. That's natural. We're professors. Does that answer your question? Cool. Anyone else before I have to dash off? No? Kim, firing shots?
Okay, thank you.
All right. Thanks so much, everybody. Sorry I have to dash out early. Again, I try to avoid being booked into large meetings with other faculty members, but occasionally they force me to.
So you might be able to be in two places at once fairly soon.
I know, right? More than just the double robot that I have in the lab, which allows me to stay home in my pajamas in my bathroom and beam into the lab occasionally.
Yeah, Jacob, you want to turn on